Good morning, physics scholars. Today I'm going to do a tutorial on conservation of mechanical energy involving the contraption called Atwood's machine. So, last week in lab, you investigated the Atwood's machine from the perspective of Newton's second law, and today we're going to take a look at it and see what we can learn about this system relying on conservation of mechanical energy. And what we'll find is we can learn a lot. We might lose a little bit of information because we're now dealing with scalar quantities instead of vector quantities, but we can still learn a lot about this system. All right, so let's do this. The problem I'm going to do right now is very similar to one of your homework problems where there's a pulley with two masses, M2 and M1. And you're given some information about the masses. M1 is more massive. Let's assign 5.9 kilograms to this mass. And M2 is only 80% as massive. 80% of 5.9 kilograms is 4.72 kilograms. So what you're told is that the system starts in a configuration that looks something like this, and then sometime in the future, let's call it moment B, mass 1 has fallen and mass 2 has increased in height, and you're told how far the masses have moved, and the distance that they've traveled, we'll call that h, is equal to 2.2 meters in the problem that I was given. So if you think about what's happening here in terms of energy, mass 2 is gaining gravitational potential energy. Mass 1 is losing gravitational potential energy. Mass 1 falls, mass 2 rises. So we can quantify the change in gravitational potential energy of the system by taking into account that mass 1 has a negative change in gravitational potential energy, mass 2 has an increase in gravitational potential energy. And we can add those two numbers together to get the total change in mechanical energy of the system. At the same time, the system's gaining kinetic energy because the masses, I didn't say this, but they start from rest at moment A and they accelerate. So at moment B, the masses have velocities. Of course, mass 1 is traveling down, mass 2 is traveling up, but when it comes to kinetic energy, all that matters is the magnitude of velocity, speed, squared. Okay, so we're going to set up the work energy theorem under the assumption that the pulley is massless, so it doesn't get any energy, and the system is frictionless, so there's no non-conservative forces doing any work, and that means mechanical energy is conserved. The sum total of kinetic and potential energy is conserved. It doesn't change. All right. Okay, so the work energy theorem says that when you go from A to B, the change in kinetic plus the change in potential, which is equal to the change in total mechanical energy, is equal to the work done by non-conservative forces. That's forces like friction and stuff like that. So I'm saying that in this case, let's assume that those forces are negligible, which means the change in kinetic plus the change in potential, which is the change in total mechanical energy, is equal to 0. This is the condition referred to as conservation of mechanical energy. Conservation because the sum total of mechanical energy, U plus K, doesn't change. Okay, so if we think about this, at the change in kinetic energy of the system is going to be equal to the sum of the kinetic energy in moment B minus the kinetic energy at moment A. So what is this? Well, we got two masses, so let's just treat them separately. So at moment B, mass 1 is going to have a kinetic energy equal to 1/2 m1v squared. And mass 2, even though it's traveling in the opposite direction, they're connected by the string So while mass 1 is traveling down with speed v, mass 2 will be traveling up with a speed equal to v. So they both have kinetic energy, and we can add them together. And at moment 1, over here, or sorry, moment A, everything starts from rest. So Ka is equal to 0. All right, now what about the change in potential energy? Well, here we're dealing with gravitational potential energy. And the change in gravitational potential energy is going to be proportional. You know, if you think about the way we calculate gravitational potential energy, it's weight times vertical position. So if you go from one place to another vertically, the change in gravitational potential energy is going to be equal to weight times the change in vertical position. Okay, well in this case, the change is equal to h, the height that the masses move. But let's erase this. So let's think about this as the change in potential energy is the change in potential energy experienced by mass 1 plus the change in potential energy experienced by mass 2. So what is that going to be? Well, mass 1 falls, so it loses gravitational potential energy equal to its weight times h, the distance it fell. Mass 2 rises, so its change in potential energy is going to be equal to its weight, m2g, times height, and it's positive because it's going up. So mass 1 gains, mass 1 loses potential energy, mass 2 gains potential energy. All right, so now we can put this all together. The principle of conservation of mechanical energy says that if you add delta K and delta U together, you get 0. Okay, so you'll have delta K is, let's factor out the 1/2, and what we see is what we really have here is, if we want to know the kinetic energy of the system, what matters is the sum of the masses times the speed of the masses squared times 1/2. So in other words, you know, what I've written up here factors to this form. And we could also factor the potential energy. There's a G and an H common in both of those terms. So factor those out. And then we have a positive contribution from M2 and a negative contribution from M1 since it falls. So this factors to that, and that's equal to 0. Okay, so I haven't even discussed, you know, I'm just writing out general equations which describe the system. Haven't even discussed what we're actually trying to find. In this problem, what you're asked to find is, well, what's the speed? What's the speed of the system? What's the speed of the mass? M1 falling, M2 rising, after M1 has fallen a distance of 2.2 meters. So that means we are solving for V in this equation. So solving for V, given the quantities that we know, you end up getting, I'm going to just skip that algebra, solve for V, subtract that from both sides, multiply by 2, divide by the total mass, take the square root. All of those things are given to us and known. G is, of course, let's use 9.8 meters per second squared, acceleration due to gravity, and you end up getting a result of approximately 2.19 meters per second. All right, so that's the answer to the first part of this problem. The second part of this problem has you use to try to figure out what the tension in the rope connecting the two masses is during this period of acceleration. And without using Newton's second law, using our understanding of energy. And of course, energy is connected to work, and work is a function of force. Okay? So the way we can figure out how much tension is exerted on one of these masses, we'll pick one. Let's pick M1, okay? And then what we can do is we can say we will write out an expression for the work done by the forces acting on M1. And there's two of them. There's gravity, which pulls down, so that's going to be doing positive work, and the tension force, which pulls up, so it's going to be doing negative work. And the work energy theorem says that the total amount of work that's done on this mass, M1, is equal to, do you remember? The change in kinetic energy. The change in kinetic energy, which now we can quantify because we figured it out. We figured out how fast mass 1 is traveling. Okay, so the key to getting this problem right is you need to restrict your scope to just one mass, okay, and quantify the work done by the forces on that mass, and one of those forces is tension. It's unknown, we can solve for it. Okay, so maybe what we'll do here is draw a new picture. Right, here's mass 1, and draw a little bigger, mass 1, and it's falling, so it experiences a displacement delta y equal to 2.2, am I using 2.2 meters, and the forces acting on mass 1 are gravity, which pulls down, and there's a tension force, we'll call that Ft, that points up. So if we think about the work energy theorem, in the first day of studying this, we said the total work done on a body is equal to its change in kinetic energy. And the total work can include work done by conservative forces, such as gravity, work done by non-conservative forces, like tension. But if we add the work done by gravity and the work done by tension together, we're going to get the change in kinetic energy. Another way of thinking about this is, well, the total work is equal to, work is force times displacement, so the total work is equal to the total force, the net force, times displacement. And there's a dot product here, but here the net force, because this thing is accelerating downward, gravity must be stronger than the tension force. The net force is pointing down, the displacement is pointing down. So we can ignore the dot product because the cosine between those two vectors is 0, or is 1. The angle between those two vectors is 0. And so the net force is the force of gravity minus the force of tension, okay, if downward positive, times the change in y, which is given to us as h, and that's equal to the change in kinetic energy of this mass. Okay, so the work energy theorem gets us started in this way. So let's just fill out the form of these forces a little bit more. The force of gravity is the mass times g, m1 times g. The force of tension is unknown. The change in y is h. And the change in kinetic energy, what's that? That's 1/2 m1 v squared. And we just solved for v in the previous part of this problem. So we know everything in this formula except for Ft, so we can solve for it. And Ft is going to be equal to, maybe I should do this in a couple steps so I don't make any mistakes. Let's divide both sides by h, and then subtract 1/2h m1 v squared from both sides, and that will equal the force of tension. So, look at this, what we really have, maybe we should have been a little bit more this is the force of gravity, and this right here is the change in kinetic energy for mass 1 divided by h. Okay, so but we know everything. We know everything in this equation except for Ft, so we can solve for Ft and end up getting 51.4 newtons. 51.4 newtons. All right, so if we repeated this analysis with using mass 2 instead of mass 1, we would get exactly the same answer. We should get exactly the same answer because the rope is connecting the two masses. It transfers the force of tension from one mass to the other, and Newton's third law. So we have equal magnitude forces on these two bodies because it's transferred by the tension in the rope. Okay, so I hope this is helpful and gives you a new perspective on a problem you've seen before, the Atwood's machine problem, from the perspective of conservation of mechanical energy and work and kinetic energy and potential energy. Okay, so the work energy theorem is a powerful tool for problem solving, and in situations where there are no non-conservative forces like friction or air drag that do work on the system, then the mechanical energy is conserved. And in this case, yes, there is this tension force, which is a non-conservative force, but from the perspective of energy, the first part of this problem, that force was internal to the system. Okay? What we were interested in is looking at the system as a whole, and when you look at the system as a whole, there's no non-conservative forces that do work on this external non-conservative forces that do work on the system. So mechanical energy is conserved. All right.